Right. Well, I am Dr. J.D. Armstrong. I'm the Maui Technology, Education, and Outreach Specialist. And I appreciate you all coming here for the University of Hawaii Institute for Astronomy's Mai Kalani lecture series, which is a lot of words for saying, hi, I'm me and welcome. Yes. We could talk about me, but that's probably pretty boring, so we'll go ahead and start talking about exoplanets because that's what everyone really came to hear about, right? Okay. So, first of all, this is an image that was provided by the Planets Consortium. It's an artist's rendition of maybe an advanced civilization on a distant world might look like if we could zoom in and see its sun and another planet in there. And that was, some of you know Dr. Berdugina, thank you. Dr. Berdugina's, Dr. Berdugina, it's her daughter that did this, and so kind of nice. So let's start off with what are exoplanets. And I would say that exoplanets are planets that do not orbit the sun. Okay, I'm not going to say whether Pluto's a planet or not. We don't have to because we're not going to detect Pluto outside of our solar system. Scientists claim they've discovered about over 3,000 of these exoplanets, and the question is, how do scientists know about these things? All right, let's start off with some real images. I have a lot of, I've done a lot of work with students on the Pholx Telescope North, and in particular, a lot of students have done some exoplanet work. So these are actual images from the Pholx Telescope North, and this bright star down towards the bottom, there is an exoplanet orbiting that star, and I'll show you some evidence of that. The question is, where is the Pholx Telescope North? It's here on Maui. It's near the summit of Haleakala. That's great. Okay, so I'm going to zoom in on this image. And if we zoom in again, we start to see the pixelation. So the pixels, each pixel is a little photometer. It's a little device for measuring light. And then it comes across onto our screen as a point on the image. It's a picture element is what pixels stands for. And you're noticing that the star seems to extend across several pixels in this image. I'm going to zoom in a little bit further. Now we're really seeing that this star is extended across several pixels. But in actuality, a star is much smaller than 1 pixel. Okay. I did a calculation at one point, and I think I came up with about 100,000 stars would fit across 1 pixel. Okay? So let's look at a model here. If this is a pixel, here's our star, and this is the orbit of a planet that, say, is 1 astronomical unit from its star. So the same distance between the Earth and the Sun as between this star and its planet. Okay, but we should remember that the star is actually a lot smaller than this. And so that's a little more like it. So there's the orbit right in the center of that pixel. Okay. Now, that's not even for a very distant star. This is actually for a fairly close star. If my animations will go correctly, but apparently not. There we go. So this is for a very close nearby star. Okay? And so if we're trying to detect an exoplanet, that's not good. All right. So let's start with a few assumptions. First of all, does physics work the same way on another planet as it does here? I think it does. And that is an assumption. We have not been to another planet. We don't know. But we have some evidence. We have pretty good evidence that that's true. Okay? And the statement also includes things such as chemistry. Okay? Chemistry can be thought of as a consequence of physics. So chemistry is also included in that statement. We're also going to assume that we have a pretty good understanding of science. We don't have to have a perfect understanding of science, but we have to have a good enough understanding of science that we're not missing something essential to this. We're going to assume that stars are objects similar to our own sun. We have a lot of evidence about that. I gave a talk on that a few years ago, or maybe it was earlier. Yeah, it was about a year ago. And we also noticed that the sun is fairly constant. We're going to assume that stars are fairly constant. That's not necessary for what we're doing, but it makes it a lot simpler. Okay? All of this can be done with variable stars, with stars that change in brightness, and it just makes it a little more complicated. Okay. So there are a number of ways that we can detect exoplanets. We can do direct observation, where we see in the image, we see the star, we see the planet, or we just see the planet. We can do proper motion. So as a planet orbits a star, it pulls the star around a little bit. And if we look in the sky and see a star wobbling around, that would be an indication of an exoplanet. We can do Doppler shifts. So again, the planet pulls the star around, and as the star kind of wobbles towards and away from us, we can actually detect that. We also have transits. This is what the type of work I tend to do, is working with students looking at transits. And there's also microlensing, which is another thing that's easily possible with the Falks Telescope North and the Los Cumbres Observatory that owns the Falks Telescope North. They have a number of telescopes worldwide, and their telescopes can be used for this by students here. Okay, so first of all, direct observation. So this is the first method. Direct observation is, the idea is that we're going to take a picture, and we're going to see in the picture, we're going to see something that is the star, and we're going to see the planet. Okay? This tends to be very difficult because the stars are far away. You know, the universe is big. You may think it's a long way down the street to the chemists. Okay, someone else can finish that line for me. This detection method is going to have a bias towards planets with large orbits, and it needs to be a big, bright planet, because we're trying to detect the light reflecting off that planet. The farther the planet gets from the star, the less light it's getting, and so the less light it's scattering. It becomes very difficult. But if it's too close to the star, then we can't separate the image of the star and the planet. But surprisingly, they have done this. Okay, I believe this is from Keck. So what they've done, this mismatch in the black and white pattern in the center is the star. And they've used a technique to null out the star, to zero out the star. And then these three white dots that are surrounding the star, those are planets. So Keck was one of the first to do it. It may have been the first. I don't know. I don't think it's very far. It's a fairly nearby star. All the exoplanets we know of are kind of in the neighborhood, in our neighborhood as far as the galaxy is concerned. It's, if you see a picture of how far how far away we've found exoplanets, and you superimpose that on an image of the galaxy, it's just a little tiny part of the galaxy. This is, I believe this is from Gemini. This is AB Pictoris. This red dot, which they colorized red just to enhance it, that's the planet, and then over here is the star. And this is from Keck. So this was 2006, it looks like. You should be able to find that. Or not from Keck, that's from Hubble. I'm sorry, it's from Hubble. And so right down here in this little square here, you can actually see, if you look very carefully in the image, you can see a little dot, and the dot moves over a period of 2 years. So it moves from here to here, just that little distance over a 2-year period, over a 2-year amount of time. Okay. So proper motion. This is the next way. I apparently someone did this. I was shocked when I recently found out someone has actually detected a planet this way. The idea is that a star and a planet really orbit each other. They orbit, or even better yet, they orbit their center of mass. So we can think of the planet as pulling the star around a little bit as it orbits. Okay, if we see this wobble in the sky, if we look at a star and it starts doing this circular motion like that, then we know that something's pulling it around, and depending on how much is being pulled around, it would be a planet. So this is very difficult to do. While we can measure the position of a star much better, often much better than the resolution of the telescope, in other words, much better than 1 pixel, the Earth doesn't drag the sun around even by as much as the sun's radius. So the motion of the stars is pretty small, unless the planet is really large. Okay? So the detection bias here is for very massive planets, and it's easier to detect them if they're close in because you'll have a shorter period. All right? There's probably a sweet spot between too close and too far away from the star where it'll be best detected, but I would imagine fairly close in is going to be a little easier. All right. Doppler shift. Used to be that Doppler shift was the way to detect exoplanets. Now it's about 18%, ever since Kepler did their huge release of discoveries. So the idea is that we observe the spectrum of the star. We spread the colors of the light out into a rainbow, and then there are these dark lines called spectral lines, and those are associated with the composition of the star. So the hydrogen, the helium in the star. And we can measure the wavelength of those spectral lines quite precisely. But as the planet is pulled around, or as the planet pulls the star around, the wavelength, the color of the spectral lines gets changed. When the star is coming towards us, the light is going to be red shifted. The light is going to be blue shifted. When the star is coming towards us, the light is blue shifted. When it moves away from us, it's red shifted. It's a longer wavelength of light because it's moving away from us. And maybe some of you have noticed when a motorcycle or something passes you on the road, you'll hear the same effect. As the motorcycle approaches, it's a higher pitch, and then as it passes, it's a lower pitch. So, or for those of you a little older, Joey Lawrence demonstrating the Doppler effect. Whoa. Okay, good. Someone got that. All right. So there's a call out to Dr. Zach Constant in there. So we can look for this periodic blue shift and red shift of the spectral lines. And by doing that, if we see that periodic shifting back and forth, we know that something's pulling it around, and that can tell us that there's an exoplanet there. This is another way of detecting exoplanets. This used to be the way to do it until Kepler came along. All right. So again, this is a method that is it's easier to detect big planets. Also, close in, because then you don't have to have as long a data set. Okay? We can actually put a limit on how massive it is. Okay? On the mass of the planet, because we know how much mass we need to make the star move around like that. But the problem is that the signal of this Doppler shift is the velocity projected onto the line of sight. So it's only the part of the velocity that is coming towards or away from us that we actually see. Okay? So if it could have a much larger velocity, like in this lower diagram, but we only see the part that is in the direction that we're looking, towards or away from us. Gravitational lensing. There have been about 39 exoplanets that have been detected using this method. Very difficult method. The idea is that a planet can act like a lens. Okay, and there's actually has been a discussion about using the sun as a lens for a giant telescope that would have very high resolution around other planets, of other targets. So, okay, the idea is that as the planet passes nearly between us and the star, it focuses the light, and so it looks like this background star gets a little brighter, and then a little fainter. So let's look at a better diagram. You have this source star that's a distant star. You have a lens star, which is already making this more distant star look brighter. And then you have a planet that's orbiting the lens star. All right. So as the lens star comes up, it moves into alignment. You get this brightening of that distant star, and then sometimes on top of this curve here, you'll see a spike that is your exoplanet. Okay, this is difficult to understand for me, so I don't tend to do this. Transits. Now this is the most important way to detect transiting exoplanets. This is the most interesting. So what does that say about transiting exoplanets? This is what I do. That's the truth. If you want to know what a scientist thinks is important or interesting, ask them what their research is. Because a scientist is not going to research something that they don't like. If they wanted a job to make money, they're smart enough, they could have made more money elsewhere. Okay? It's because we love what we do. So, transits. We think about the solar system. Imagine we're going to fly outside of the solar system. If we fly out at just the right angle, we're going to see a situation like this animation I've got in the upper right-hand corner. Okay? The planets of the solar system will pass between us and the star. As it does, it can block a little bit of the light from the transit. When we have a transiting event, we know the geometry, we know the alignment of that orbit, and we have very precise timing. Those are two things that I really like about the transit method, is we have very precise timing. And we also have the geometry. We know how the system is aligned, which is very nice. Okay, but here's something that has kept me up all late at night. And in fact, this friend of mine in Utah that I give a shout out to earlier, he actually kind of looked at me at one point and said, "Yeah, but can you really know that there's a planet there? You've just got a dot of light." So, can we really detect a planet from a single point of light? Well, I don't know. Can we? Let's think about it. First of all, what can we prove? Somebody tell me something you can prove. You can't prove that the comment is that the sun will come up every day. No, you can't prove that. There's only one thing that I know of about physical reality that can be proven. I think, therefore I am. I can prove my own existence to me. You can prove your own existence to you. I cannot prove to you that I exist. you cannot prove to me that you exist. And if you've ever seen the movie A Beautiful Mind, here was a genius that had schizophrenia. And he saw people, talked to them, wrote reports for them and put them in a mailbox. Okay, but they didn't exist. But I do believe that you exist. I have a theory that you do exist, and because I see you, and I trust my senses, and I can test that theory. Well, hello. Okay, got some response there. Okay. So the question is, the rest don't exist? Now who said that? I'm sorry, I don't see you. Okay, I can refine this theory and see if you can speak. So when I say hello, some of you spoke back. Okay, do other people see you? Okay, Rosa, would you do me a favor? Describe the person to the left of you. What color hair? What, So dark brown hair, dark brown eyes, hairy face. What color shirt is he wearing? Blue and brown shirt. Okay. So that is consistent with what I see. And again, in the movie A Beautiful Mind, there's a scene where he meets somebody new, and so he turns to somebody he already knows, and he says, "Do you see these people?" And they say, "Oh yes, Professor, we see them." And so he knows they're real. But there's still this thing that I don't know you exist. I think you do. But this theory is becoming more and more consistent. You see that person next to you. Your description of that person is the same as my description, with variation. It's not exactly the same. So actually, the slight variations make it a stronger proof of existence, a stronger evidence for existence, because if you were made up in my mind, I would want it to agree with me perfectly. All right? Now here's something that's very interesting. Most of a scientist's time is spent trying to disprove theories. You don't really prove or disprove anything, but finding evidence where theories don't work. You want to find where the theory breaks, because that's the new science. All right. So let's get back to exoplanets, because that's what you came to hear about. Let's look at our hypothesis. Okay, we observe planets orbiting our star, right? Our sun. Okay? Is that going to be a unique situation? What do you think? No. I've seen Star Trek. Okay? They go out to these other planets. All right? We hypothesize that there are planets orbiting other stars, and we hypothesize that some of these planets will transit their stars viewed from the Earth. Let's think about what that would look like. Okay? Well, here we go. Here's an exoplanet. What I've done here is, this is the sun. And I've taken a little dot, and I've put that on the sun, just digitally drew a little dot on the sun, and then I've moved it across, and I've measured how bright the sun would be. Okay? If we viewed it as a star. And so we're going to play a game here. And the game is, there are several frames from this animation right here in the middle. We've got several frames of it. And below, I've got this graph of how bright the star is, up and down, and left to right is the time. So what we want to do is, where would we find this first image on this graph? Okay, Rosa. Yeah. Right here at the beginning. So this flat shelf at the beginning, yes, sure enough, that is. Okay? Okay, this next image, we get a little nick out of it. You've already played this game, so I'll make somebody else go. Somebody else wanted to guess where, as soon as we've got this little nick out there. That's where it starts to dip, yes. And the next one? Down even further, so maybe right here? At the beginning of this kind of bowl at the bottom. All right, what is this next image? Very bottom. And the next one? Yeah, okay. So you guys get the idea. All right. So, but there's one more question. I apparently forgot this slide. Why do we want to study exoplanets? Give me some reasons why we would want to study exoplanets. We're lonely. Okay, I like that. So in other words, we want to look for other life forms, so other civilizations, right? Go ahead, Rosa. We're curious. We're just scientific religiousness is what Einstein called that. I love that one. And then Mom back there. We can learn about our own planet if we learn more about others. Okay? Yes? To detect habitable planets. Okay, so kind of a summary is that we want to explore strange new worlds. Seek out new life and new civilizations. Boldly go where no one has gone before. Okay, so that's what we're doing here. That's why we want to do this. So here's how we do this transit method. Okay, what we do is we take a series of images. We measure how bright the star is by adding up all the pixels around the star, and then we plot that against time. Now, I've just lectured you on having solid evidence, right? So no one in here is going to tell me, if I give you a mess, I don't want anyone in here to tell me I believe that's an exoplanet if it doesn't seem convincing to you. Do you all promise that? Okay, so here's what we get if I plot how bright that star is against time just by adding up how much light falls inside that circle. Ready? There you go. Are you convinced? How many of you are convinced that that is an exoplanet? Yeah, I'm hearing not terribly. Other comments? I'm hearing regression analysis. Obviously, you know, our economist here. Okay, yeah. Yeah, you have to rule out other options. And so I'm not convincing you, am I? Okay, so yeah, maybe there's some background noise. I've been outside. I've noticed that the sky is blue. Very, very occasionally. Around here it's not been lately, but okay. So maybe, and at night, actually, there is light from all parts of the sky. At night, the sky is still blue. It's just a lot darker. Okay? So maybe our problem is that I need to get rid of the blue light from the sky. Maybe that's what's messing us up. Shall we try that? What I'm going to do is I'm going to draw a couple extra circles around here. And in this between the outer two circles, I'm going to use that to determine how bright the sky is. I'm going to look and see, I'm going to see on average how much light is showing up in each one of those pixels, because that's light coming from the sky. Does that sound reasonable? Okay. So I'm going to subtract that off. There we go. Much better? I'm seeing one person shaking her head, another person saying no, a couple of you laughing at me. Okay, well, this is getting embarrassing. Maybe explore strange new worlds. So if we can't explore strange new worlds, we won't get to seek out new life and new things. Well, everyone, turn on your imaginations. You're hearing Beethoven's first piece, Twinkle, Twinkle, Little Star. Okay, everyone hear that? Okay. So stars twinkle, and they really do twinkle. It's not a trick of our eye. It's the atmosphere acting as a little lens. More light gets directed into your eye at some times than others. Well, that'll work on the telescope too. So the star is getting brighter and fainter based on the atmosphere, and okay, and maybe there's a little bit of light cloud that passed in front of it. So the way we can do this is, let's look at a reference star. Okay, so this blue star down here, that's our target star. That's where we expect to find this exoplanet. This red one is the star we're going to use to measure how bright the blue star is. So I'm going to compare how bright the blue star is and the red star. So how many times brighter is the blue star than the red star? Or I divide the number of counts, the brightness I get on the blue star, by the number of counts I get on the red star. All right, you ready? How many of you think I'm going to convince you this time? I get one maybe, okay, three maybes out of this room. Okay, well, okay, this is starting to look believable. Okay, here's the simulated, here's the actual data from the telescope. This is honest to goodness, actual data. This is a friend of mine when he was in high school. He was doing this work, and this is actually his data that he was working with. All right, so that's fairly convincing. But now wait a minute. We've got two stars that we're measuring in there. Maybe it's not the star that I'm saying the transit is around. Maybe it's that other star that's changing. I don't know how it's changing, but changing in such a way to make it look like a transit, okay? Because it could happen. So we're going to use a control group. We need a control group. So what I'm going to do is, you see that green star? I'm going to treat that exactly the same way as I treated the target star. That way, if the red star is changing, it'll show up in this green star as well. Okay? Okay? If everything is proceeding as the way we think it should, then we would expect that when we plot how bright the light is from the green star, if we make this light curve for the green star, it should be flat and straight, right? There we go. Transit up to the left, simulated up to the right, the control, the check star, down to the bottom. No, that does. The question is, does that mean that this check star does not have a planet around it? No, it could have a planet around it. First of all, it might not be the time that star had a transit, or it might not have transit. It could the orbit could be out of the plane of our observation. Okay, so all this is saying is this other star is behaving well, and the reference star is behaving well, so that we can use this to measure the transit. Okay, is everyone good with that? Wonderful. So, if this is a planet, are we just going to expect one transit? No. So I'd better be able to show you that it repeats at least once. We need at least 3 before we claim it's a planet, before astronomers will say, okay, go ahead and publish that, that's a planet. And I can even do better than that. There's the 4th one. And what Travis, this friend of mine, was working on when he was in high school is he was looking at the timing of these transits to see if he could actually detect like a moon orbiting that planet that might be pulling the planet around in such a way that we could detect it. How do we know it's the same planet? That's a very good question. Because we see a transit every 2.15 days for this target. The depth of the transit, you'll notice, is very similar. Okay, 0.55, 0.55, 0.55, 0.55. Okay, the transit depth is the same. The duration of the transit is very similar to within, you have to give me some noise here, but the shape of the transits are generally fairly similar as well. Why aren't they yeah. Okay, so why are they not exact? This is number 3 that you're talking about being very different. This one, it looks to me almost like we had some clouds or some problems with the camera, because it looks like there are not as many observations in the same span of time as these others. Okay. There can be differences in if you change the camera, if you change the telescope, if you use a different filter, if there's cloud in the sky, and one of the things I want to work on with a student is characterizing how reliably we can detect the depth of the transit and the shape of it, because that's actually kind of important. But yeah, go ahead. Yeah. Up on the right, yeah, that edge, it does seem kind of skewed. I've got to agree with that. The fourth one, the transit looks deeper. Yeah, yes, you're right, it does. Mm-hmm. Yeah, so the skew, my guess would be I would try to explain that with a star spot. There might be a star spot that's developing there. And actually on number 3, the bottom here is not very well rounded, so I'm guessing there were some star spots at the time, and that's what was transiting it. A lot of these details, yeah, I don't quite know why it's kind of skewed like that, except for it could be that we have a drift in the overall brightness that has not been properly removed. 2.15 days, Earth days. We'll get back to that. Put a pin in that one. Okay. For any of you who want to play this game at home, I would really encourage you to go to the Los Cumbres Observatory Global Telescope Network. They have an awesome program called Agent Exoplanet. And when I first made this talk, it was in the beta stage. I think it's fully developed now. And you can actually, they have real images. You can go ahead and make these measurements. They made it pretty easy. And you can see this for yourself and do it for yourself. So, what does it take to find an exoplanet, to discover it? Takes a telescope, yes. Okay, I've been working with a telescope called CORAL. It's no longer operational. It's a satellite telescope. CORAL stands for Convection, Rotation, and Planetary Transits. It was put into orbit by a collaboration between the French Space Agency and the European Space Agency. And the idea of this telescope, this satellite telescope, was that it could do very precise photometry, and it had a very large field of view, so it could look at a lot of stars. But it could only see things that were about 15 arc seconds by 25 arc seconds. So that's sort of the resolution of the pixels. So let me show you, and I'll show you that in a minute. This is a picture of the satellite. Okay. And here's the rest of the team. So this is Alexis and Regina. Connor's actually a student here on Maui. This is an old picture. I'm glad Connor's not here to be embarrassed. Oh, yes, he is? Oh, good. Hi, Connor. So I make it worse and wave at him. Okay. And Malia. So these are students who actually did this work and and Connor is there. He's going to kill me afterwards, I know it. All right, so the rest of the team is the Phoenix Telescope North. And to give you an idea, this is me. I was actually up there repairing the telescope, and Rob Rakowski happened to be up there, and so, you know, Rob and his camera are never far apart. So thanks again for that picture, Rob. So here's what it's like. Okay, so the coral follow-up. I remember how I said the resolution was about 15 arc seconds by 25 arc seconds. The resolution on the Phoenix Telescope North is about 1 arc second. So the size of these stars, the way to measure the size of those stars is it comes out to be about 1.1 arc seconds. So for comparison, this is how big a resolution element on Coro is. So this image would kind of look like this in Coro. All right. Now, okay, somewhere in here you've got an exoplanet-like event. So was it on this star, or wait, where did the stars go, right? You can't really tell. Somewhere in there, there's a transit. That's what Coro can tell us. So your task, should you choose to accept it, is tell me. So I'm going to give you a hint, and this is actually Connor's data. I think this is your data, isn't it, Connor? I'm pretty sure it is. So the transit, we only caught the second half of the transit. Okay, based on the predictions from Coro, we only got the second half of the transit. Okay, is that star the one with transit? Okay, is that it? Yeah, not a whole lot. Yeah, let's see if any. Yeah, it could be, but yeah. Is that it? Yeah, does that look like the yeah, the last half? Yeah, and that was it. And the Coro team actually put down these guys as co-discoverers on a hot Jupiter. So something similar to TRES, or to WASP-2b that I like so much. Okay. Pardon? I don't know what the period of that one was. I'd have to go look and see which. I don't even know what they named that one. They would have named it Coro and then a number to designate which discovery it was. Okay, so great. We know that we can detect exoplanets, right? We're fairly convinced. Are you fairly convinced that from a dot of light I can tell you there's a star orbiting? Good. With transits with the transits, we can actually determine the size and the period. And with our assumption that we understand stars and gravity, we can tell how far it is from the star. So if we know how far it is from the star, how big and bright the star is, we can tell how hot that planet is. So now, without ever seeing this planet, I can say what the temperature is like, what the weather might be like. And this isn't just a wild guess. This is actual, physics. Okay? So let's start off by looking at our solar system. I want to get back to our solar system. This is from NASA. And in the center is on this left-hand side, the outer ring is Jupiter, and in the side is Mars. Then we've got the asteroid belt between Mars and Jupiter, and then we've got the Earth, Venus, and Mercury is in closest. And then over on this side, we see the whole solar system. So Is our solar system very common? Yes, I heard a quiet yes out there. Someone didn't want to commit. I think I heard a no over here. Again, it was quiet. Oh, no idea. Okay, good. Commit to that one. No, I don't know. There is nothing wrong with the I don't know. So let's look at this WASP 2b exoplanet in comparison to our own solar system. So this is just the inner part of the solar system. It's kind of at an angle. It's kind of tilted. We're not looking at face on. The Earth. How long does it take for the Earth to orbit the Sun? 365 days. Okay, good. Good. I'm not lost this crowd. Venus. How long is a year on Venus? 225. Good. We can get people reading. All right. I like that. We got a reader here. Okay. Mercury. 88 days. Remember and notice there's a trend. The farther away, the longer it takes to go around. If you want to know more about that, you could look up Kepler's laws. And it could give you mathematical predictions and all sorts of fun things. So, the closer to the star, the shorter the period. It's got less distance to go around, and it actually moves faster. I said 2.15 days for WASP 2b. So it's really in close to its star. About out of hell. Yes, they have meatloaf every night for dinner. All right. So it is really close in there. How hot is that planet going to be? Very hot. Yes, Rosa, thank you for raising your hand. I was reading your mind, though, and you had the right answer. No, I am not still reading your mind. Stop thinking that. Okay, so 2.15 days. It's really close to its star, very hot. I would have to look and see what type of star it is. This is kind of assuming that it's sun-like, but I don't care. Even if it's not a sun-like star, it's got to be really close. Okay. Do you have a question? Yeah. Yeah. Yeah, but I thought Connor had his hand up. Okay. Flash flood warning. Okay, till 10:15, everyone. So we'll watch out the window. Okay, Connor, you had a question? Shh. Oh, yes. Because I changed it in this slide and forgot to change it in this slide. So there's one typo so far. I should have had Connor proofread it. Yes. Mm-hmm. Mm-hmm. Yeah, so for a Jupiter-like planet in a Jupiter-like orbit, it would take many years. Saturn, the orbit of Saturn, I'll go with that because I remembered off the top of my head, is 22 years. So if we wanted to say that we had discovered something like Saturn orbiting its star, we would need 3 transits, and that would take 66 years. I'm hoping to retire before then. Takes 22 years, yeah. All right. Okay. That's right. Transiting and even Doppler method, it's not great for detecting planets that are farther from the sun. Yeah. 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 The Doppler method has a real bias towards large planets close to their stars. The transit method, it's not the mass, it's the diameter of the planet. It has to be large, close to its star. And it's also easier for transit method. It's also easier if the star is small. Okay. Yeah, so it's not great for detecting planets that are similar to the Earth, you know. But it's the best method we've got. And Kepler, which is another satellite, they actually did detect Earth-like planets, but not a lot. Okay, so I wanted you to realize that there really is this big detection bias in what I'm showing you. Okay. Next thing is, now all the planets in our solar system orbit on the same plane. Okay? If you were to put all of the planets in the solar system on a table, you would only be off by maybe 5 degrees from their real orbits. Okay? And the rotation axis of the sun is fairly close to that the orbital axis of all the planets. So everything rotates the same way. And so we can actually measure the orbits, you know, what direction the stars or the planets are orbiting if they're transiting. That gets into a lot more complicated thing. And so you have this star, which is rotating, the front here is rotating off to the right, and you have the planet, which is going kind of the other way, but it's also tilted. Yeah, almost going over the poles of that star. That's very different from our solar system. There's a lot of them that are like this. Okay? Some of them going backwards entirely. And then there's this system where we have two planets that are kind of making an X. So our system, our solar system, might be fairly unique. Okay? So, somebody recognizes that. Good. So, what does it take to support life? Yes, I'm reading your mind again. Yes, water was right. No, I will stop on food. Yes, okay. But food doesn't grow without water. Main thing is we need water, and we want it to be in 3 phases. We need it to be in liquid. Okay? But based on reality, you're also going to get it as a solid, and in our atmosphere, it's as a gas. Okay? Here on Earth, we have this triple point of water: liquid, solid, and gas. And we think that's probably necessary for life. So that sets our temperature that we need. Okay? For water to form, the planet cannot be too close to its star, or it's going to be too hot. It can't be too far from its star, or it would be too cold. It's got to be just right. So they call this the Goldilocks Zone. Yes, exactly, the Goldilocks Zone. All right? So, but there is something, you know, if we're going to be really honest, I have to say that without the atmosphere, the temperature of the Earth would be about freezing. We would be too cold for liquid water. So, neglecting our atmosphere, we're maybe not inside the Goldilocks zone. Okay? And the greenhouse gases are what changed that. Does anyone know what the strongest greenhouse effect gas is? You said carbon dioxide? Nope. Methane is stronger, but it's at such a low level that carbon dioxide beats it out. What's the number 1 for the Earth? Water vapor, that's right. Water vapor has the biggest effect on greenhouse effect on the greenhouse. Yeah. All right. I'm going to skip this. How big is too big? Probably we want to go between twice the mass of the Earth and down to maybe 80% of the mass of the Earth. And a lot of that requirement comes from the need for liquid water, enough of an atmosphere to have liquid water, and also from if you get too big, then you start heading towards the way of Jupiter. Okay. This is the famous Drake equation. When I was in high school, I first saw this, and I thought this was really cool. The idea of this equation is to use what we know about stars and planets to calculate how many intelligent civilizations there might be in our galaxy. If you want to, you should go into this. Go to Wikipedia. It's got a good explanation of it. But the idea is that now that we're detecting these exoplanets, we can actually start to think about whether or not there is other life in our galaxy. And how close would those neighbors be? If you put numbers into the Drake equation, they're probably less than about 100. I didn't actually do it. I read somewhere. I was reading a reliable source. They were saying, oh, probably less than 100. Okay, so we'll use that. About 100 civilizations in our galaxy. Okay, so there's also a habitable zone for the galaxy. If you're too close, you've got other stars whizzing by, disrupting your solar system. If you're too far out, you don't have enough metals to form the planets and form life. So there's sort of a habitable zone for the galaxy, and that's about 25,000 light years from the galactic center. I don't know how wide it is exactly, but let's just assume we're going to spread these 100 stars out on this 25,000 light year circle. And that would mean, on average, we would expect our next door neighbors to be about 1,500 light years away. Okay? How many miles is that? Lots and lots. That's the, oh yeah, I billions and billions of miles. Oh, sorry, that's already taken. I guess I'll go with trillions and trillions, which is what he suggested be the next evolution, by the way. So our average, on average, 1,500 light years away. So would they come all that way to visit us? Well, first, if they knew we were here, they might come. Okay, this is not getting in the car and driving out to Hana. This is a long way, 1,500 light years. Okay, 1,500 years to get here at least. So, if they knew we were here, they might come this way. The light bulb was invented in 1879. That's not long enough to go 1,500 light years. Okay, radio was invented a little bit before that, so maybe if they were looking for our radio waves, but they're still too far away to detect that. Another reason they might come here is they could see that, oh, there's oxygen in this planet's atmosphere and other signs that this is a habitable planet. Someone was saying, let's look for habitable planets. So they might come if they were planning on staying. Okay. If Trump's president, well, maybe that's proof that they did stay. Okay. I think most of Washington, D.C. might be proof that they did stay. But if they came here, of course, they would talk to their friends back home, and they would want to send a picture of what this typical Terran landscape is, and this is what they would send, right? 70% of the Earth is water. So they would say, this is what our home looks like, our new home. All right. Now, in a further argument, I hope most of you are familiar with Richard Feynman, who's kind of one of my heroes. And so let's listen to what Dr. Feynman said about the possibility of extraterrestrials visiting us.
I had a conversation about flying saucers some years ago with laymen. Because I'm scientific, I know all about flying saucers. So I said, I don't think there are flying saucers. So my antagonist said, is it impossible that there are flying saucers? Can you prove that it's impossible? I said, no, I can't prove it's impossible. It's just very unlikely. That, they say, you are very unscientific. If you can't prove it impossible, then how can you say it's likely, that it's unlikely? Well, that's the way, that is scientific. It is scientific only to say what's more likely and less likely, and not to be proving all the time possible and impossible. To define what I mean, I finally said to him, listen, I mean that from my knowledge of the world that I see around me, I think that it is much more likely that the reports of flying saucers are the result of the known irrational characteristics of terrestrial intelligence rather than the unknown rational efforts of extraterrestrial intelligence.
So in case you did not hear that, Feynman's comment, the final comment on there, that he thought it was more likely that the reports of extraterrestrials, of flying saucers, were due to the known irrational nature of the human mind rather than the unknown rational efforts of extraterrestrials to reach us. Okay. So, we do think that there is intelligent life out there. We just don't think it has visited. All right? And so there are ways that we could detect other life, and I'm not going to go into this in great detail. We could look for radio waves. We could look for the lights of the civilization. Okay? We could look for a heat signature. This is one way that Dr. Kuhn has suggested, and some of you have heard him talk about that. We could look for the atmosphere. In particular, if you can look for spectral lines, you could detect things like oxygen that you don't expect to find without life. Oxygen's very reactive. It tends to get tied up in other compounds. And so you need something to generate oxygen. So he is working on a project called Planets. And this is there are a number of us here who are doing it. I'm a little more fringe than some of them. Of course, okay, the minute I said that, I knew someone would comment. Planet stands for polarized light from atmospheres of nearby extraterrestrial systems, which if any of you follow the S.H.I.E.L.D. television show or the S.H.I.E.L.D. saga, it's the reason it's named Planets is somebody really wanted to use the acronym Planets. All right. But it's a very nice acronym and very much says what it's going to do. The idea is to look at the polarization to filter out a lot of the noise and try to get the atmospheres of these nearby extraterrestrial systems. And we can only go out to nearby. This will be a 1.8 meter telescope, a lot of new technology. If you want to find out more about it, you should go to planets.life. And I'm just noticing that this belonged on another slide up there. So we will skip this animation. But this is the idea of where WASP-2b is. It's this big planet in very close to the sun. But go to www.planets.life to learn more about this. And I'm going to show you a quick video very shortly here. The Feynman video is part of the Feynman lecture series. If you Google Feynman and flying saucers, this video will come up. Okay, so I'm going to, this video is on planets.life. If I can get it to play. There's no sound on this, so if you're not hearing any sound. Apparently there's no video on this either. There we go. Okay, this is a work in progress. And this is part of the Planets Consortium. This is a movie to show some of the interesting things with the Planets Consortium. This first telescope is the Planets telescope that they are talking about building, 1.8 meters. Notice that the telescope is off axis. This eliminates those spikes that you see in Hubble images, so you can look much closer to the star. Okay. This is ELF. These mirrors are each about 5 meters in diameter. You get a lot more resolution with this. Again, they try to avoid any on-axis type of thing. But when you want this much area, you need to start putting them all the way around. This next, the next one is Colossus. This will be, is it 76 or 78 meters in diameter equivalent? Is Kevin here? 76. We think it's 76. Somebody can double check us. These are our concepts that are they're being designed. Where will they be built? To be determined. So this is the Colossus array, and one of the ideas, what I think generated this idea was the need for a 1 kilometer square telescope for the Starshot project, which is an idea of sending microsatellites over to the next star. It's that difficult and that difficult to do. Go ahead and read about it if you want to learn more about it. I really encourage you to go and take a look. How much money are we talking about? Colossus, I heard, was somewhere in the neighborhood of $1 billion. It's a very specialized telescope. So on the one hand, it's not out of range of the cost of the latest, biggest telescope. Now, we've been talking about building the 30-meter telescope on Mauna Kea. The next largest one is about 40 meters. This is, doubling the size. So it's a lot. It's a much, much bigger telescope. You would expect a much, much bigger price tag. But the fact is, it's a specialized telescope looking only at a very small part of the sky because you're only interested in that one star and what's going on around that one star. So you can make a telescope and guaranteed you're going to find $1 billion worth of science from this telescope. There's no doubt about it. Whether or not they find what they were looking for, I think if anyone's got a shot at doing it, these guys do. But guarantee that if that gets built, it will be easily $1 billion worth of science. Okay, where were we? So, our goals. I said that we were going to explore strange new worlds. Did we do that? All right, I'll check that one off. Seek out new life and new civilizations. Okay, I got a thumbs up from Rosa. Boldly go where no one has gone before. That's kind of, yeah, you're kind of half-hearted on that. Let me see if I can't get that one checked off. Okay. One of the questions I get asked about as an astronomer is, what's the most exciting thing you've seen? Okay, first of all, they ask about black holes, and then they ask about ET. And I'm talking to you about ET. I don't do black holes, sorry. They're cool, but yeah, let's go look for ET. So what's the most exciting thing I've seen? Okay, this is an image from the Falks Telescope North. I took this, Maui Astronomy Club was up at the summit with me. This was taken on November, so the 11th month of 2011. The right ascension of Jupiter on that day was 11 hours, 11 minutes, 11 seconds. The declination was 11 degrees, 11 seconds, or 11 degrees, 11 minutes. Thus proving Jupiter is the loudest planet in the universe. 11. It goes to 11. So anyway, Jupiter, this is, and you can see the moons of Jupiter, and this last one, you see the red, green, blue, because it's moving between each of the colored filtered images. Okay? See, nebulas. This is, pardon? Yes, trapezium. Or some of my friends like to call it the Falk's Phoenix. This is an image from the Falk's telescope, and you can kind of see the wings of a phoenix in there. Okay. Hey, if you see the crab in the Crab Nebula, that's a phoenix, man. You do not have to be on as high a dose of drugs to see a phoenix in that. Okay. Globular clusters. So just millions of stars. This little knot of stars is a globular cluster. It's probably the core of a galaxy that we've seen. So what do you think is the most exciting thing I've seen? Which image? Maybe all of them? Jupiter? Who else has a guess? Go for the globular? Well, I'll get back to that in just a minute. Okay, some people connect to nature with emotions, you know, and that's not a bad thing to do. Do not take this as a criticism. They go out into the wilderness and they feel. But scientists also connect with nature. Okay? Instead of just going out and having a feeling of connection with nature, we use more of who we are. We apply logic, mathematics, many years of education to really make a better connection with nature. And so I'm going to tell you that science is really about connecting with nature. This is the most exciting thing I've seen. And very seriously, when I saw this graph the first time, I hadn't even given the data to Travis yet. I was so geeked. Okay? The simulation came after this. Okay? I saw this transit, and I just thought, look, it's a planet. And so I started, in my mind, painting this picture of, okay, I know what this planet is like. It's orbiting its star every 2.15 days. Okay, I've made a deeper connection than you can make without these tools in mathematics and logic. Another thing I'm going to say is that science and engineering. There's a difference between science and engineering. Okay, and this will lead up to my final point, which is coming up. This is a friend of mine, Jamie Foxx, told me this. It's not the actor-comedian Jamie Foxx. Is a friend of mine on island. He may not have been the first person, so if I am quoting somebody else, please let me know. If you're an engineer and you do not know what you're doing, you need to stop because you're doing the wrong thing. Okay, does anyone not understand that? Does anyone not follow that? Engineers need to know what they're doing. If you are a scientist and you do know what you're doing, you need to stop because you're doing the wrong thing. And so I was up at the summit of Haleakala a few weeks ago with my intern, and I was explaining to Mark Elphick, who's the site manager for the Falk's Telescope North. I said, you know, I'm a scientist because, and I said this, and Erica looks at me and says, looks at me, looks back at Mark and goes, he's being honest. He doesn't know what he's doing. He is a scientist. Thanks, Erica. Just feel the love. I hope you're watching. I just feel the love here. But that is what science is about is that you don't know what you're doing. You don't know what you're going to get into. Science isn't about, oh, wow, come look at this, eureka. It's usually more about, huh, that's weird. That's where the real science gets done. Okay, so this is my favorite image because I don't just see a bunch of points here. I see that planet. And so science is boldly going where no man has gone before. Thank you. Yes. How do they discover exoplanets going around binary stars? I almost am tempted to pass that off to Nakoa in the back. He's just started working on a project about that. Same way as individual stars. So you have two stars, they're orbiting each other. In close, you could still have this transit. WASP 2b, they believe, is a binary star. Last I checked, they were saying they believed it was a binary star. Yeah. Yes, and so Dr. Mark Willman, as he just pointed out, there are two cases. One, orbiting around one of the two stars, or second, you can have the two stars and then the planet orbiting outside of them. I think it's fairly difficult to detect the second case, isn't it, Mark? I don't know that they've even, I think they may have detected one or two, but yeah. Yeah. So yeah, if you're going around both stars, the transit method is almost certainly out. You can use the Doppler method. You might be able to find it with the Doppler method. But it's very it becomes very complicated, very difficult if it's not orbiting just one of the two stars. Okay. Yes. Yeah. So the question is that in science it's usually a cardinal rule that if you have a hypothesis, it needs to be falsifiable. And yeah, I very much see that as valuable. I could sit here and argue that what I was seeing in that dip was actually Marvin the Martian pointing his ray gun at the star every 2.15 days. It's not falsifiable, but it's also not science. If you can't falsify it, if you have to invoke supernatural, then it starts becoming bad science. You need to be able to test, because science is about, like I said, science is about connecting with nature. You can make up all sorts of things in your head, but if they're not part of nature, then it's not part of science. You should be able to test it. Yes. So well, so the question is a debate over using the "I think, therefore I am." I think we need to debate this. We'll sit down and talk about it. Okay, that's based on Descartes. Yes. Yeah. No. So the question, yeah. So the question was that Descartes later changed it from "I think, therefore I am" to "I am, therefore I think." But I don't necessarily think that that's true, because just because something exists doesn't mean it thinks. A rock does not think. But yes, but it does, just because you are doesn't mean you think. Okay, and which again takes us back to certain political figures we won't mention. And the other thing is so anyway, we'll let's discuss that later. That's going to be an argument I can see. Been asking for a while, or waiting for a while. Yes. Right. So the question is, the WASP-2b that orbits every 2.15 days is most likely tidally locked, correct? Mm-hmm. Right. So the rest of the question is, planets that are tidally locked are not considered a good place to find life because of what it does to the atmosphere, but you're not sure what it does. Right. So, okay, let's imagine if the Earth were tidally locked. Okay, this side, which means that the same face of the planet always faces the star. So the moon, yes, the moon is tidally locked around the Earth. If you watch the moon over one full cycle, you'll always see the same side of the moon, because as the moon orbits, it rotates at the same rate it's orbiting. And that's not a coincidence. We can explain that through physics, and it's based on the tides slowing down the rotation of the planet until it matches the. So the idea is, tidally locked, one side of the planet is receiving all the energy from the star. So it's it's very hot side, and then you have a very cold side. Okay, well let's go somewhere in between. Let's go to the twilight of the planet. There it should be nice and pleasant temperature-wise. And you have wind. You have the one side of the planet being heated up. The atmosphere heats up, rises up, and then goes over to the other side, and the cold and cools off, sinks, and then rushes along the surface, causing gale force winds constantly. Their trade winds are, 100, 200 miles an hour. So it would be very difficult. I think it would be very difficult to develop there. Okay. Yes. So how many planets have been discovered that are in the Goldilocks zone? I don't know. What's the closest one to us? I think it's Proxima Centauri. But again, Proxima Centauri would be tidally locked. So I don't think it's a very good example of where to look for life. The other thing is, Proxima Centauri is a red dwarf. So red dwarfs tend to flare up quite a bit. And so you've got this planet that's very close in because it's a small star going through very strong flares. It probably is not the best place for life, but I could be wrong. So, yes. Mm-hmm. Mm-hmm. So the question is, you watch science fiction, you see other ways of traveling, because if traveling in normal space limits us to the speed of light. And so they use wormholes, and I assume you want to talk about hyperspace or warp drives. Wormholes would require tremendous amounts of mass and energy in order to set them up. I don't know how we would do that. Yeah, so it's related to a black hole, except for a black hole is just in. A wormhole is a stretching of space and time so that you have two points in space that are connected with a tunnel that's shorter than the distance between them, in theory, it could be done. I don't know that it's practical or realistic or. Hyperspace is sort of like leaving our universe into this parallel universe so that you can go faster. That's very. I'm very skeptical of that. The warp drive, NASA is working on something related to that, and currently they've got the energy consumption. They think they could get the energy consumption down to something like if you took a VW and converted all of the mass into energy, then you would have enough to do it. But converting that much mass into that much energy, yeah, it's beyond our technical capability at this point. So that might work. An advanced civilization, I still think I'm going to throw out wormhole, and I'm going to throw out I think I'm going to throw out hyperspace. I think those are unlikely. Warp drive, maybe. I don't think we're going to get to the point of Star Trek where we're going between stellar systems in a few days. I think it's going to be years at least to get to other star systems. It's going to take a very long time. And it's going to be a very unusual thing because it will require such a tremendous expenditure of energy. Okay? You can't just take mass and convert it into energy. You have a limit on what fraction of mass that comes out of nuclear physics and conservation laws and that. Maybe there's a way around them, but I think it's going to be require tremendous effort. I think it's possible, but it would require tremendous effort. All right, you've in the back. What was Pluto doing on my thing there? Yeah. Yes. So the other thing is that is required is we probably need a magnetosphere to protect the life from the stellar winds, and you need the stellar winds to protect the life from cosmic rays. And the magnetosphere potentially is detectable. And actually, Connor, we were trying to look for signature of that, as you remember. So yeah, it is potentially detectable. All right, let me go way in the back before your hand falls off.
Yeah, getting back to the concept of light,
Mm-hmm.
forms of water,
Mm-hmm.
the Goldilocks Zone, those concepts. And you're making the assumption that light requires different types of water. And you don't bring into the equation the possibility that light may not require that type of element combination. In other words, it could exist as methane, using methane or using a type of acid or using some form of substance that
Yeah.
we don't
Yeah.
exist. Can you just elaborate on that a little bit?
Okay, so the question, let me see if I can get this in a good nutshell, is I assume that we need water for life. And maybe we don't need water for life. Why am I arguing that we need water for life? Is that effectively? So let's say liquid methane or liquid nitrogen. Okay, liquid nitrogen. We've got this in the lab. Some of you have come in and played with it. It doesn't dissolve very many elements. The value of water for life is that it is a catalyst for a large number of chemical reactions, which is why almost every chemistry lab you'll see a lot of water being used because it facilitates these chemical reactions and allows that life to develop. We don't know of any other compound that is so good for creating allowing chemical reactions to proceed. And so without water, you have options for chemical reactions. It could exist, but I think it's unlikely. I think it's much more likely that you're going to find water as the basis of life. They've also examined whether or not carbon versus silicon could be the basis of life. We're carbon-based. Silicon-based life, there was in fact, one of the Star Trek episodes talked about a silicon-based life form, and Dr. McCoy is not a bricklayer, as we remember. Silicon could be used. It has a lot of different combinations, but they're coming back around from what I'm seeing and saying carbon is the way to go. So there's a bonus to answer to your question. I hope that wasn't unappreciated. All right. Yes. Tardigrades. Mm-hmm. 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 Yeah. Okay, let me go to so the first was your comment that maybe a magnetosphere is not necessary for life because tardigrades in particular are particularly resistant to radiation. Also, scorpions, I believe, and cockroaches. And so they're going to, so, after World War III, we're going to have a bunch of cockroaches running around eating Twinkies and on sugar highs. It's going to be great. So yeah, it is possible for life to develop without a magnetosphere. But again, I think it is harder. It's more difficult. It's possible. Some of the criteria for life are possible, and some are required, I think. Water is somewhere on the borderline of required. It might be possible. Magnetosphere, you probably want it. You probably want it. The size of the star also, people argue that you probably are not going to develop life around dwarf stars versus supergiants, because supergiants get a lot of ultraviolet light and X-rays, and that breaks chemical bonds and makes it very difficult for life to develop. Small stars, you have to be in so close that you get in all these flares. And your next point was on the tidally locked. You have this very narrow strip of where the temperature of the planet is just right, and yeah, that's part of the problem, is that strip is very narrow. You could develop life there, but I think it's very unlikely. So did that answer the rest of your question, the second half of your question? Okay, yeah. Okay. All right. Anyone else? Okay. We'll go ahead and continue this with other questions in a little bit, and anyone who wants to go can leave without feeling bad. I hope you know you can